All right. So we are at time now. I'll start. I extend a very warm welcome to all of our guests on this panel and to the audience who are joining us for this online session. My thanks to the Stockholm International Water Institute, the organizers of World Water Week 2022, for giving us this platform to showcase all of our work. This session, near real-time water risk forecasting, enabling a transition to water-prudent power production, is co-convened by World Resources Institute, Vasudha Foundation, and Growald Climate Fund. I'm Sahana Goswami, the Senior Program Manager with Urban Water Resilience at WRI India. We begin the session with a presentation followed by a moderated discussion, and a panel of experts. Krishnan, Associate Director Program at World Resources Institute, Vinuta Gopal, CEO and founder of Asar Social Impact, Dr. Sukanya Randhawa, Advisory Scientist for Auroville Consulting and the lead AI researcher for social good at Heidelberg Institute for Geoinformation Technology, Dr. Lucas Krutwagen, early career researcher in geography and the environment at the University of Oxford and co-founder of Oxford Earth Observation, OXIO, an environmental risk intelligence startup. And finally, Brinda Sharda, an independent consultant with Vasudha Foundation and an instrumental member of the team developing the Vasudha Power Info Hub. And we'll hear a little bit about this platform in a little while. Our presentation has 4 parts, and I'll begin with a broad overview of the water energy nexus and why we find this an area requiring urgent action. This will be followed by Brinda and Lucas speaking on the Info Hub and the reservoir forecasting model, respectively. The presentation ends with a short video of the reservoir dashboard, which is now live on the Vasudha Power Info Hub. Now, there are a couple of perspectives we can take when we talk of the water energy nexus. There's water required to produce energy, or the reverse, there's energy required to produce or treat water. And while in this presentation, we speak more about India, because that's where the research and our study has been focused, what we realize is much of our learnings could be applicable and relevant anywhere across the world. Our world has an abundance of water, but a really rather minuscule proportion of this is fresh water, which is available for us to use. And India, again, has only 4% of that available fresh water. This is a very limited resource, and it must meet all of our needs, whether it's drinking water or producing food, running our industries, and indeed, even for generating power. India remains heavily dependent on thermal power production. Around 62% of the entire energy mix for the country is thermal. And this particular type of production system is extremely reliant on the availability of fresh water. And increasingly, we see that climate change-driven extremes are breaking these rhythms that we have had of long-established rainfall patterns and really disrupting all of our plans which center around consistent water availability. Yet we cannot really say that we deprioritize the power sector, reduce water allocations if there are issues and conflicts. Because at the end of the day, whether it is our agricultural activity, it's our industrial performance, indeed all of our urban lives, they are so contingent upon our ability to continuously have access to power. It's not really alarming on how sensitive the thermal power sector is to water deficits. So we have earlier research by WRI, which has established that 40% of India's power plants are in high water stress zones. Water shortages between 2013 to 2016, a mere 3 years, cost of India's top 20 thermal utility companies, causing an estimated loss of around $1.4 billion. So this main challenge that we see that emerges when we apply this nexus perspective to the power sector is this increasing uncertainty in water availability, which is really causing so much of our disruption. And this is a particular vulnerability primarily due to the setup we have, which is a high proportion of our production being water dependent thermal and feeding into a large centralized grid. Now, I do want to point out here that India is not alone in facing these risks to power production. And it is not just thermal power that is at such a risk. Just recent news over the past few weeks has highlighted that power production, whether it's nuclear or hydro, whether it's in China or all across Europe, is very disrupted this year because of high temperatures, drought, dropping reservoir levels, and so on. And so that's the challenge. But one would, the reaction to this would be that this crisis point brings about new ways of us thinking and imagining how the power sector should continue to work to be effective and efficient in a climate and water uncertain future. So being able to plan for the vagaries of a few months ahead, and at the same time acknowledging that disruptions are going to be much more long term, and how do we chart radical plans to change our pathways? And eventually, one hopes that the outcome from all of this thinking and re strategizing would be that the new pathways will ensure that water is to power production, and therefore water is to the subsequent development impacts that we have are mitigated, so that water is not so much of a stressor for us. And eventually, that we're able to provide equitable water entitlement for all users. So to further this end objective that we have of enabling a transition in the power sector to more water-prudent methods, we believe at WRI that a key lever that can be applied is the availability of transparent, open access, and near real-time water risk information and forecasting data. So if we, and we further describe this water prudence not merely as tweaks in water efficiency to existing production, large scale will be triggered by having access to water risk and water stress data can guide this transition to low or no water dependent clean energy, particularly in areas which face freshwater stress already. At an operational scale, we can talk of a reduction in freshwater dependent thermal power plants, whether it's through retirement of existing facilities or improving water use factors, and finally ensuring that equitable water use remains. And power production, despite it having this very crucial status to development, that it does not usurp the rights of other users, which are equally critical. And to enable such a transformation of the sector, which is ambitious and it requires the participation of a lot of players, in fact, pretty much everyone needs to be a part and parcel of making this change, whether it's policymakers and investors, who are the guiders of how money flows into this sector and where money flows to, whether it's operational decisions at the reservoir or power plant scale on how water availability is there and how production schedule should be mapped. And finally, an aware and vigilant civil society, whether it's community groups or media who can demand more water secure futures. But to be able to do this, what we want to do is also have this tying together through the availability and access of data, of open access, transparent, and credible data, which will eventually empower whether it's citizens or decision makers and enable evidence-based decision making. So now, having brought into the conversation the need for data and information, we will next hear from Vrinda about the incredibly rich database that Vasudha Foundation has created for India's power sector. And after her, Lucas will give us a brief on the predictive model that has been developed. So over to you, Vrinda. Screen, you can.
Yeah. Thanks, Shahana, and good afternoon, everyone, to people who can see us and we can't see them. I am glad to the World Water Week and WRI to given this opportunity to talk about the Vasudha Power Info Hub. Shahana, so would you help me take through the slides? Shahana?
Sorry about that. Should I go ahead?
Yeah, I can't see the presentation deck. I think you're not shared. You have to share again. Yeah, thank you. So quickly taking this opportunity to introduce Vasudha Foundation. It is we were set up in 2010 in India, and we are been leading policy advocacy and clean energy market enabler, and been working with the not-for-profit objective to ensure and provide access to clean, sustainable, and affordable 24/7 energy for all. We work across 4 verticals, primarily power and climate change being the main focus areas, and urban infrastructure as transportation is something that we have started working on lately. Over the years, We have worked with a number of utilities at the government, at the state level and the national level, also the financial institutions and other stakeholders. Next slide, please. So about the Vasudha Power, so it's actually a data powerhouse that we are trying to create, and I'll talk about in more details when I go to my next slide. But this is something the Vasudha Power Info Hub aims to bring together the comprehensive, integrated, historical and current data on electricity sector across the value chain, which includes generation, transmission and distribution of power in India. And here you can see the homepage where it actually looks at providing you the quick numbers that anyone would need on the sector value chain. It further dovetails information on other cross-sectoral areas, which includes plant technology, water availability, air quality of around the power plants, environment-related aspects, as well as the other socio-economic indicators such as per capita electricity consumption, per capita income, etc., to present a comprehensive picture of the power sector transition, that it's not only independently working in silos. There's a lot of other factors that actually impact the working of the sector. Next slide, please. So coming on to the background for the initiative. So what we felt is that a lot of data in India that we find in terms of granularity is behind paywalls, and we need an open source knowledge platform to actually discuss and provide a comprehensive power sector picture. Then also, there was a lot of challenges that I think a lot of CSOs and think tanks would agree here in tracking multiple government dashboards and portals and other set of reports that come. So there was a large difficulty in extracting those large and unprocessed data sets. Next slide. So these are quick dashboard snapshots if I have to take you through. So this is where anyone could get a quick understanding of where India's power plants, how many number of power plant units are operating, what is the number of retirement power plant unit, what is the corresponding capacity to it. And again, in this India power map, if the second row, the first picture, if you see, you will find that how many number of operational power plants are in India, what is the capacity, which number, what is the number of solar oil. So that all you can get at a click. So that's the level that we wanted to do in terms of providing data access and availability to our users. This again on the right and second bottom line, the DISCOM graph. So what we are trying to do here is to look at what is the source of information for different electricity utilities, what is the source of power, so which power plant is it seeking its power from. So it maps even some of those elements individually for almost 60 to 70 DISCOMs which are there in the country. Let's go forward, Shani. Next slide. So yeah, I'm very happy to share this with this global platform that NITI Aayog, which is one of India's apex public policy think tank, actually the only apex public policy think tank, has adopted the Vasudha Power Info Hub, and now which will be called as the India Climate and Energy Dashboard. And this is since it's in the development phase and is going to be launched in the by the end of this year. So this is a quick sneak peek of how the kind of data that we're looking at. So it's basically not just energy or power. It's not just power, but it's going to look at the existing India Energy Dashboard, which was there by India, where it was looking at the energy data sets and then merging up with the Vasudha Power Info Hub and adding more information on climate and energy. And it's going to also look at tracking the progress of various other timely schemes, initiatives that keep coming, and then tracking them in terms of the RE targets, in terms of its updated NDC. So that the tracker is going to look at, the dashboard is going to provide all that information to the users. Next slide, please. So the vision basically is the entire vision of this entire initiative is to make this as a one-stop platform for all the kind of stakeholders, for all the energy, climate, and associated economic data sets which are relevant to India. And it's going to basically foster evidence-based research, developing a user-friendly and dynamic platform that is providing easy data access to ensure that the data is high quality, and to also facilitate the confluence of various dashboards and analysis and ground level research that is happening in different parts of the country to put that in one centralized format. Next slide, please. Next slide. So the objectives is going to be essentially to, so here this was created for the India's climate and energy modeling fraternity to act as a backbone of it, act as a backbone where, you know, the data, there have been data gaps, and also bring a variety of stakeholders together to build this data gaps and granularity issues. Next slide, please. Some of the features, if I have to take you through, so there is enhanced visualization and interactive graphs. If you go on the website, you will find that it's not just limiting itself to some Tableau versions. It's based on Mongo database, and it has a lot of, and the kind of graphic library that we have followed is also high quality. So you will find a lot of SWOG graphs, and that can be used for presentations, that can be used for better analysis, better visibility, etc. Then there is an interactive analytics section, which does not look at only a sector in silos, but also try to bring together various elements of the power sector, energy sector, and climate sector together, and see that the kind of impact it's going to have, a particular set of data is going to have. Then another is there will be continued granularity and contemporaneous of data. And then it's not just the time, the temporal granularity that we're looking, we're also looking at the spatial granularity, that we're not looking at only national level data sets, but we're also looking at state level, district level, at some cases, in some cases, and also DISCOM level, as I just described in my slides before. Next slide, please. This is just a quick sneak peek of the ICD homepage, which they're going to look like. So this is the first is my homepage, which talks about tracking the India's updated NDC. Then there is a graph which talks about how sectoral emission trends have shaped in the in the case for India. Then there is another which talks about economy, what has been my GDP, what has been the trends, then demography. So this is just a homepage sneak peek. There's a lot more interesting things that we are looking at, and we'll be happy to share with the forum some details later. But right now, the Vasudha Power Info Hub is only limited to the electricity sector and its value chain data. This is just, I think we can skip these slides. I would just take this opportunity that when we started working on the slides and when we started working on the dashboard, one thing that we found was that how you bring those cross-sectoral linkages, and where then it was at that point of time that we recognized that, you know, WRI brings that expertise on looking at this providing this predictive modeling for power plants and for water intake at power plants. That's when we collaborated, and we're happy to see this coming to fruition. Thank you. Over to you, Lucas. I think these are few just snapshots that I wanted to take, but not taking much of the time. But this is what all, I think the link for the website, for the dashboards at the front of the slides. And please have a look and do share your comments and inputs on the section. Thank you.
Wonderful. Well, thank you so much. Yeah, hi everyone. My name is Lucas. I'm happy to talk now about the predictive model that we developed to predict water availability in 11 reservoirs to begin with, but actually we deployed this over quite a larger number. Basically, all the reservoirs that we could get hands on the data for. I'll talk about that now, and this is all work that's coming from the Wave to Web hackathon that was organized by WRI India and others last year. So it's been a long journey to get to this point, and it's been really great working together with everybody on the call to bring this to life. So Yeah, so let's dive in. So I want to first just start talking about the problem statement as we understood it, and just where we started in terms of using a machine learning approach to be able to predict surface water availability in these reservoirs. So previously, what you would have to do is you'd need to take sort of extensive in situ measurements in order to characterize the hydrological cycle in a given water basin. So not only would you need to know sort of the meteorological forcing data, which is sort of the precipitation, the evapotranspiration, the temperature, you'd also need to sort of characterize everything about a given water basin. So things like land cover, surface, the slope, which is important for determining surface runoff, and also things like geology and below ground conditions in order to characterize those infiltration and percolation water flows. And so this was quite a job to do. And so wherever you wanted to do this kind of predictive work, you had to take a lot of in situ measurements. But now the current state of the art is to use machine learning to sort of parameterize and learn these in situ parameters for each water basin. And all we need then is some sort of observed measurements of some part of the hydrological cycle, and then also, of course, the meteorological conditioning data. And so here, this is a wonderful figure from the neural hydrology Python library, and we're, of course, building on the work of others, particularly at the University of Natural Resources and Life Sciences in Vienna. But this is where we started, and we said, I think there's all the data here that we need to do at least to start at predicting surface water availability, just using meteorological forcing and the reservoir measurements. So next slide, please. And so that's precisely what we did. We assembled the data that we needed. So we took the basin geometries for the reservoirs that we were looking at. We also then collected the historical water levels and water volumes for the reservoirs of interest. And we began with 4 reservoirs in the Wave to Web Hackathon scope, and then expanded that to 11 reservoirs later as we were looking at integrating with a Water for Power dashboard. And then finally, we just said, well, look, the API is there, let's get all the historical water level data that we can. And so we got, I think, 66 reservoirs in the end. And then we collected the meteorological forcing data as well. And the trick for us was that we wanted this to all be done in near real time. So we wanted to put into operation something that would be able to continue to provide water availability predictions moving forward. And so not only did we need to collect sort of the historical, all this historical data to train the machine learning model, but we wanted to then be able to make predictions that were kind of periodically updated so that this was useful for as a prospective decision-making tool. So next slide, please. So just to kind of dig in a little bit on what we mean by hydrological basins. So we're using the Fafstetter system, which describes the boundaries of a hydrological basin. And the beauty of the Fafstetter system is that you can sort of zoom in and add different levels of basically a hierarchical nesting of water basins, and you can zoom in as far as you like to individual streams and whatnot. But we sort of picked a Fafstetter level that gave us that seemed to match the catchment area for the reservoirs that we were looking at, and then we assembled these into networks of hydrological basins, because we know, of course, that water availability in one reservoir has a lot to do with the water that's available upstream and downstream. And so we wanted to characterize this problem not of one of predicting individual reservoirs, but of predicting actual reservoir networks and basin networks. And so in the end, we assembled I think 10 or 11 basin networks that were sort of linked individual reservoirs. And when we designed our prediction problem to work on the level of a basin network. And then for each reservoir, you can see here the data that we've collected. So we've collected the CHIRPS rainfall product, we've collected AR5 land from ECMWF. And importantly, we wanted to collect some forward-looking data so that we had some conditioning from a forecast as well. And so we also collected the TIG ensemble mean forecast. And so those two products are from the European Center for medium range weather prediction, and CHIRPS is from UCSD. And then, of course, we are collecting the reservoir levels from the India Water Resource Information System, and we did that across all reservoirs. And so there's some data cleaning, of course, that we had to do. But just to clarify, we're showing time series here. These are the sort of spatially reduced means of the sort of the upstream area of each of the reservoirs. So, this is the average temperature, for example, of an upstream area of one of the reservoirs, or the average precipitation over the same area. Yeah, next slide, please. And so here's our actual model. And so this is a deep learning model, and we were inspired by the NLP, so natural language processing type models, where you're trying to predict sentences or words in a sequence. And because we knew we had sequence data, we wanted to, we thought that was a sensible place to start looking at some reasonable methodologies. And we were also, of course, inspired by the work of others who have been doing similar work. And so you can see here, this is a sequence to sequence to sequence model. And so a sequence to sequence model is where you have two sequences of data, and you're going to pass an encoding between two sequences of data that allows your machine learning model to kind of learn the relationship between the different sequences. And so in our case, we had three sequences of data. We had a historic encoding period, we had a forecast period, and then we had the rest of the prediction horizon. And so the hackathon was a 90-day prediction problem, so about 3 months. And we also then had sort of quite a long period of historic data that we could condition on. And so this historic period, we took historic temperature, historic precipitation, and used a Bayesian LSTM to develop an encoding. That encoding gets passed to the period for which we have forecast data, which is 15 days. And so then we use the forecast data to continue to condition. And then we pass another encoding onto the prediction period, which is the remaining 75 days. And so we don't have any forecast data for the rest of that period. And so all we have is sort of the day of the year periodicity that we can use to then use the encoding that gets past that last sequence to decode it into our predictions. And you can see, I won't go through the entire line diagram here, but you can see that we're using, so we have an autocorrelative model. And this means that we pass the reservoir volumes as an input, and our prediction problem is just to predict at each time step the reservoir inflow and outflow. And this was important to us because we thought in the operational context, you would actually know how much water was currently in the reservoir. And so the prediction problem should be more about how much is going to flow into or out of the reservoir. And also in similar contexts where these kinds of models have been used for other time series problems, quite often you are trying to just predict the difference rather than the absolute level of your regression target. So that made a little bit more sense to us. But one thing that we thought we did, which was particularly interesting, was we used some graph convolutions in our decoder. And that captures the relationship between the upstream and downstream basins. And so we have this matrix A here, which is the hydrological adjacency between the different reservoirs. And so we sort of, for each reservoir network, we trained this model. And so the end result is 10 different models for each reservoir network. Next slide, please. Like I said, we wanted to put this into production and provide sort of near real-time predictions. And so we had to build quite a bit of infrastructure in order to do that. And so sort of moving from right to left here, we have our sort of raw data sources, which we then ingest, and we ingest them with a bunch of cloud run services that are scheduled on tasks. And then we store that data either as tabular data in BigQuery or as gridded data in ZAR archives. We have a library that does geospatial reduction on the gridded data. We have a machine learning repository that we use for training the machine learning models, and then also for inference. We cache everything that on sort of the outside of BigQuery. and that allows an API to pull that data in real time. And this API is all publicly accessible. And then we serve that up to our own sort of little dashboard, which we submitted at the end of the hackathon. Next slide, please. And just some quick results. This is kind of what the results look like. And so you can see here in pink, this is the actual observed data in 3 select reservoirs. And then going from light green to dark blue, you can see the extended time period. And so you can find a lot more of these results and a lot more details we prepared a preprint paper and put that on Earth Archive. So you can see the link here. You can access the code base, of course. There's a GitHub org and 8 different repositories where we've kept all the code for this work. The data API is publicly accessible. There's some documentation that you can find. Our own dashboard is up there, and then you can also find the data frames that we used for the actual machine learning work. If you want to just jump into the machine, like trying out the machine learning model yourself. You don't have to do all the data work. You can just grab the data frames. And I think that might be the end for me. So yeah. Anyway, yeah, it was a really great hackathon. Yeah, we were a small team of University of Oxford students, and this has been a really exciting project to be a part of.
Great, thank you so much, Lucas. And as Lucas and Binda mentioned, that this was really a confluence of many things that came together, that and opportunities that we were able to leverage. The fact that Vasudha Power Info had this existing dashboard, I were able to run a hackathon on similar lines. Really see that this is reservoir water level information is something that is so relevant for the power sector as well, that we were able to bring all of it together. And now we have the dashboard live on Vasudha Power Info Hub. We'll share a short video, just a couple of minutes long, to give you a quick peek into what it looks like. So I'll stop sharing and over to Anu to share hers.
Yeah, thanks, Anna.
Thank you, Anu, for sharing your screen. And many thanks to Madhura from WRI who actually put this video together for us. So we'll move on to the moderated discussion piece now, and hopefully my internet stays better because I think there have been some glitches a little while earlier. My first question is to Deepak. You were the co-author on WRI's working paper, Parched Power, and this research really brought to the fore the water energy nexus and the very tangible impacts that we see because of water variability on power production. So I would really call upon you now to give us a little more of a perspective as an energy sector practitioner on how this water energy nexus really plays out in power production. And I think this really ties into the whole theme of this conference of valuing the unseen, because within the power sector, water is such a crucial component, and that is something that we seem to lose track of at times. And along with that, maybe you could reflect a little bit more on how the learnings and our understanding that we derive from the Parched Power research, all the interactions that we had with a variety of stakeholders really helped us conceptualize this Water for Power project and led us to this point where we thought of developing this predictive and forecasting tool. So over to you, Deepak.
Sure, Sahana. Thank you, and hello, everyone. Glad to be here and look forward to the discussions. So the study that Sahana referred to is called Parched Power. Essentially, it started off as trying to look into the Central Electricity Authority used to report statistics on how many power plants were not functional in a particular year due to lack of water. So that got us thinking into seeing, is there a pattern at certain times of the year? Are there particular plants that repeatedly shut down every year? And we started looking at what is, and then the idea was to extend it and see how if we consider all the thermal power plants as a whole, how would that reflect on the water stress for India's power sector? Keeping in mind that the nation has invested so much of money into building these power assets, whether it is private, publicly owned, and the results are there to see in terms of how much the power and energy deficit have come down from the highs that we had at the beginning of the last decade to what it is now. So when we started looking at it, we found that unlike in the case of EIA, in the case of the US, where every power plant also reports its water withdrawal and consumption, in India no such ready-made statistics was available. If at all, there were some numbers from sustainability reports of the companies that were reporting it plant-wise, and if we were really unlucky, they were reporting it at a company level. Or else we would have to refer to the detailed project reports that were prepared at the time of environment impact assessments of the plant during the time of construction. So that is where we had to go back to the drawing board and come up with a technical foundation in terms of using satellite imagery of the power plants to see what kind of cooling system is there, what is the fuel that it is using. And then look to literature, India-specific literature, which was also available, to see if we could provide the intensities of water withdrawal and consumption for each of these power plants. So using that and with the trained algorithm, we were able to project some numbers on as far as India's water stress due to all the types of power plants is concerned. We were able to observe the shift from once through cooling to recirculating cooling. We were able to assess the impacts of that, and that one of the numbers which Sahana showed in her presentation, about 40% of the power plants being in water stressed areas. That stark number did come out as part of the study. And this also coincided with what the Ministry of Environment and Forest was trying to push onto power plants in terms of water consumption norms and air pollution norms simultaneously. And this is where, again, Sahana, your point about valuing the unseen comes in, because if you go to a policymaker with a conversation on air pollution, that's definitely something they're ready to have, because it's something they see, smoke billowing out, cities submerged in smog. So that's something a relatable problem for them. Whereas water, they knew at the back of the mind that it is a issue, but the ready willingness to jump to tackle it, like in the case of air pollution, was a little more difficult to obtain. So we also came out with some of the findings, wanting the MOEFCC to impose those norms a little more strictly, enforce mandatory audits, get the power plants to also shift to air-cooled technology, which even now is not significantly high within the power generation mix. So those were some of the recommendations that we had. And following that, as you rightly mentioned, we also did an on-ground outreach to different stakeholders, the generators, financial institutions, civil society. And there are some nuances also when we talk about water shortage. One, for instance, even situations like where the cooling intake of the cooling system is not functional, it gets reported as a water shortage. So some of the power plants were of the view that there needs to be some more granularity in terms of how these metrics are captured. Building on this, we also looked at about 5 listed power companies, and saw how the impact of water stress is there on their balance sheets and profit and loss statements. And we also used the IPCC's 5th assessment report. That's when the study came out, to project, in case of future climatic issues, what would be the potential impact on these power plants. We found that depending on the company and the location of their plants, on a quarter-to-quarter basis, there was a negative EBITDA effect of about 0.07% to even close to 17.5% in the case of some of the companies. So there is certainly a significant financial impact which is there, and that is a very powerful messaging tool that can go out to companies and investors. And that, I think, is the foundation for Water for Power, which takes a more real-time view with a 90-day horizon, rather than a static kind of scenario upon which these projections are built. So it's a sequential progression, but I think we are in the right space wherein we are looking at more real-time solutions to help people even operate their plants. I would hope for.
Great. Thank you so much, Deepak. And if we have time, of course, we'll try and pick up on some more of the points you have flagged. Just leading off of that, my next question is to you, Vinutha. Again, given your role with Asar Social Impact and sort of the engagements you have been doing for the power sector and on the social sector, so I think there's a confluence there. So my question to you is this, that of course this is a predictive model that we are talking of. There's forecasted data around water availability, and so I'm assuming this is of interest to power plant operators. So there's this inherent scope for efficiency improvements we can talk of, and I think Deepak touched upon this a little bit, but who else would you flag from your experience would be users of such data in the power sector, and how do you envision, again from your learnings with interactions with them, of this sort of information, how does it help effect change among these other users who might be there in the power sector? Over to you, Vinutha.
Thank you so much, Sahana, and congratulations to WRI and Vasudha Foundation for coming together to, I think, sort of bring together and make visible this intersection between water and power. I think it is extremely important. And as you pointed out and Deepak pointed out, making this information visible would definitely inform decision makers and policy makers in ways that would ensure, hopefully, that we are looking at planning our power generation in such a way that we are not exacerbating a local water situation. So I think that's really essential, and many congratulations for having come together to do this. I mean, what we have also observed, I mean, like Deepak said, when you saw that there were power outages and the CEA was reporting that certain power plants had to be shut down, the other aspect of it that one also noticed was very often you would also see agricultural stress in these regions. Many of these water stressed regions are also in the water basins, of course, are also agriculture, where we are using some very often very water intensive crops that is being grown. For example, in Maharashtra, there are the sugarcane. Sugarcane is a crop that's grown in similar regions where also power plants exist. And there is definitely contestation of a shared resource between these different users. And I think the first sort of impact very often is seen on agriculture, because agriculture also depends very heavily in many areas on access to surface water and as a backup to groundwater, because groundwater involves, of course, greater costs. The other aspect, I think, is when the problem really gets very intense, then it affects access of water even for drinking and other purposes. I think many of us would remember, for example, that Maharashtra actually even asked for shutting down of billboard lighting at one stage when there was power scarcity. And the power scarcity was not necessarily because of a scarcity of power plants, but because they could not run the existing power plants because of water shortage. And so we are, I think that there is this intersection is really important to acknowledge and plan for. I think the data that 40% of our power plants are in water scarce regions and fairly seriously scarce regions is something that definitely, even states need to take into account when they are planning their power situation as well as their water situation. And I think it's also going to become really important to overlay the climate impacts now possibly as another layer over this, because we are going to see the situation get even worse. And it's already showing already in multiple parts of the world, we're seeing drought-like situations with entire river basins drying up. So what impact is that going to have on our future power? So I think that it's really important to acknowledge this is an issue. This is this planning requires intersectional stakeholders. So it does require definitely agriculture to be a part of this conversation. In addition, of course, to the water resources ministry as well as power. And this needs to happen even at the local levels, not just at the central government level, definitely at the subnational level, and definitely even lower levels of governance. So I'm really looking forward to this model being shared a lot more widely with decision makers, including, like I'm saying, at even district level with collectors and so on, because I think it's quite critical information for them to know and plan for.
Right. Thank you so much, Vinuta. And thank you for laying out that context, because it really helps me segue into what I wanted to ask Sukanya next. Sukanya, I want to sort of turn on and draw upon your thoughts on this reservoir predictive tool. And Vinuta's given this perspective of this really myriad of other users who are critically dependent on water as well. And I wanted to ask, particularly from your experience with the Lifelines tool that has been developed with you and your team at Auroville Consulting, how do you sort of bring in socioeconomic layers and context to some sort of these sort of very technical AI/ML tools, so that there's this really localized context is built in, and that really helps improve the impacts of these sort of forecasting tools that we would want to use. So over to you, Sukanya, and your thoughts on this.
Yeah, thanks, Sahana. Vinuta did cover a lot of points that I wanted to say, but I'll still go ahead. So I think this tool is great. Predicting water reservoir volume levels are very useful numbers to have, and it's kind of I'll go to the other applications later, but just for the water reservoir itself, having a forecasting tool like this is great, because in 2018 in Kerala, if you remember what had happened during the monsoons, they had to suddenly release water, and we had like 5 million people affected, and Kerala was large parts of Kerala were completely flooded. So if you really look from a climate risk or disaster management point of view, and just look at the reservoir alone, I think this is a great planning tool for them, to really manage water levels. So not just having real-time sensor values that would tell them just the real-time stuff, but having a forecasting tool that could be then coupled and for really planning and better management of reservoirs. So that for one. And then and then of course, if you really look at everything that goes downstream from the reservoirs, right? So the water, like Vinita had mentioned, is used obviously for agriculture. It's used for other industries downstream, apart from power. And so I would say for both these aspects, for really informing and optimizing irrigation schedules for water intensive crops or other crops, and also for so like I said, other industries. So there's this aspect that definitely, if you have water volume numbers for the reservoirs, these could be really used for planning interventions downstream for all kinds of water management activities. And what is also interesting is that apart, we are thinking only, of course, in terms of water quantity here, but water quality is also very much interlinked. And if you think about, so many times for a lot of religious festivals that happen downstream. Just 1 second. For a lot of activities that happen downstream, what they do is they just release the reservoir waters to dilute the water quality to kind of make it accessible for people. So I mean, not the best thing to do, but again, it's another intervention that could really be used for really diluting the water quality, if in case also for agriculture or for other activities, because there've been many instances where water quality has affected the farmers and the produce, and and the entire ecosystem. Actually, there've been heavy metals and things like that. So that's one. And then I would say really, since as we move forward in terms of climate change, we are seeing more erratic patterns in weather. And specifically, if you really look at the cyclonic storms that have really increased in the global south all over, and so I mean, these kind of predictions are definitely useful to kind of plan better. Of course, it really depends. Of course, we'll talk about in the other round about how will the tool is able to really deal with these kind of erratic, weather patterns, so to say. Coming to Leela. So a Lifelens, Leela is short form of Lifelens, the project that I was working for at Auroville Consulting, which is a non-profit organization. So there, the idea was that we were using, satellite imagery and GIS mapping and AI tools for really identifying lands that are unused, and then doing a suitability assessment to find lands that were best suitable for solar deployment, for sustainable water management, and for ecological restoration or forestation. So I'll just post a link later, and you guys can go over that later. But we use almost 40 to 50 different global data sets. Some of them we derived ourselves using satellite imagery. And the idea, again, from socioeconomic to really physical context of the land, and the environmental context, of course. So coming back to socioeconomic, I think things like if you really were to look at disaster risk management, if you were to look at layers like population or the census data, so really population at risks, for example, or then kind of that's one thing. Then there are things like water demand that could be very interesting in terms of, so on one side you have the, when we talk about water management using these numbers from the water reservoirs, then on the other hand, you also have water demand, and that both things could be coupled in, for example, right? So, so I would say, yeah, so risk management, population numbers, and of course, there's a whole lot of census data. So all of that could be plugged in, and I think it would be a very interesting tool. And there's a lot of scope as we move, go forward with this kind of data.
Great, thank you so much, Sukanya, and really thank you for flagging the point about these different sort of water users within reservoirs. And initially, that was one of our ambitions within this project as well. But we found that was one of the most difficult data points to get. And because per reservoir, who are the different users and what is the share is so contextual, and it changes season to season. It might change politically. So it was a really complex thing for us to be able to get that at this point. But that is definitely something we want to explore as we engage with other stakeholders and get more local information. Thank you for your thoughts on this, Sukanya. Lucas, I'll turn to you now. And you have, of course, given us quite a lot of detail about the predictive model. And even from this, it's quite clear there's an incredibly complex model that has been developed, learning techniques, and if I understand it, the model, it learns to improve itself. But having said all of that, of course, there are limitations as well. So maybe you can help us understand a little bit about, how do we interpret model performance? Why there might be variations in results across the 11 studies reservoirs. And I think that's one of the audience questions that have come in as well, to understand how it might be performing across different geographies. And when we interpret these results, how do we go about doing it? That if a result is not, meeting a certain threshold, do we just discard it, or do we look for what these reasons might be? So tell us a little bit more about how this model works, and how best we can interpret what it is telling us.
Sure. Yeah, thanks so much for the question, Sana. Yeah, I think it's so important to not treat this kind of predictive, these kind of predictive models like oracles. And we know that there's a lot that, if we were to do it the same work again, we'd do it quite differently. We learned a lot while we were doing it. But I can give a bit of an idea of what the performance of the model is across different reservoirs, and how we should treat that. And so the first thing I think I wanted to emphasize was something that the other speakers have talked about as well, which is that this problem of predicting water availability is, there are supply side considerations, but there are also quite a lot of demand side considerations, and there's feedback loops between those as well, right? So if the temperature goes up, then there is more evapotranspiration, and there's also more water demand for irrigation, for example. There's these two sides of the equation, and a lot of what we've done has only really looked at the supply side of water availability. So there's I think a lot more detail and work to be done on the demand side, but then also this is one of the major drivers of uncertainty, I think, in our model results, which is that water demand will differ so much between different water basins, different reservoirs, different sort of points in the reservoir network, and of course that also gets traversed through the reservoir network as well. So if there's a lot of water demand downstream, then that's going to have some effect upstream. So so this is one reason why the performance might be different. And then there's and so what we've tried to do with our model is we used a Bayesian LSTM, and that means that every node in your neural network is actually represented by a distribution, a standard distribution. So it's sort of a mean value and a standard deviation. And when you sample from your model, you can actually sample from those distributions. So you get sort of you get some degree of uncertainty in your model results. And so we tried to do that to communicate the various levels of uncertainty. And part of the problem is that you have to, in order, you still want a reasonable sort of maximum likelihood estimator, and so you're trading off this relationship between ability to to predict sort of the mean and then ability to characterize the distribution. And so it's quite difficult, and we had to make trade-offs. And so yeah, I think there's just a lot of variability between these different reservoirs. One thing that we saw a lot was deviation to the sort of climatological mean. And part of that we wanted to make sure that the model was aware of, for example, the day of year periodicity, and could then make inferences about okay, what is the average for for a certain reservoir at a certain time of year. But this might also be missing the key application, right? You might have seen in some of the results our model does a good job at predicting reservoir emptying, but doesn't do a particularly good job at estimating when the reservoir will fill again. And perhaps that's a more critical question, because maybe it's really the end of the dry season that is the most critical or something. And so getting that fill date, or getting that what is the date in the year by which 50% of the reservoir capacity will be refilled. This might be something that is actually a more interesting problem than just kind of the raw predictive, like X many days in advance prediction problem that we did. But I still think we made a really good start at it, and I think also predicting differences, like day-on-day differences, was a good way to go. And so you can see how that uncertainty gets propagated into the across the prediction horizon. But yeah, really, it's not. This was kind of a first effort, and we certainly shouldn't be treating these results as an oracle. But yeah, just demonstrating that this technology is on its way, and I think hopefully we've signposted what the next steps for work are.
Great. Thank you so much, Lucas. And truly, as you say, much of the technical details are a bit lost on me. This isn't my area of expertise, but in terms of the visuals that we get out of it, and that's powerful. That's really powerful. And having a sense that even if we don't take that as the absolute certainty of this is what is going to happen, it still gives such a clear indication of what the future might look like. That I think is going to be definitely powerful information for a lot of users. So thank you for your work on this. So I'll move on now to you, Vrinda, and I think just in the interest of time, just keeping a watch, that we do want to take some of the questions that we have from the audience as well. I'll wrap up some of the additional questions I had to you, Vrinda. So we have this Power Info Hub, which is developed by Vasudha Foundation. This is amazingly powerful information center, and I have spent a few hours on this and quite immersed in all the information and visuals you get. It's a bit of a rabbit hole, because you're just sort of looking at information and connecting dots and looking at other stuff. But please tell us a little bit, two things that I want to ask you. One is that you have about half a decade experience of running this platform. Vasudha, as a Power Info Hub, has been there from about 2018. And you have had a lot of users of this data. Can you tell us a little bit about how and if there have been, how users have used this information, if it has led to any sort of changes in practices, or differences in how outcomes are happening? That's one. And the other is, what makes you optimistic that all of this that we are putting together, this reservoir dashboard, putting out forecasted data on water availability, what makes you optimistic that people are going to use this and that this will add value? So one is a little bit about your past experience of how it's happened, and one is looking a bit into the future of how you envision things, would get used. Over to you, Vrinda.
Great. Thanks for the question, Shana. And I'll first look at the first part of the question is the journey. So the journey, if I have to in a nutshell say, the journey has been definitely a lot of hard work that has gone into creating this website and creating this dashboard, and taking it piece by piece and joining it from the highest national level to looking at the DISCOM level distribution. So and then again looking at the data inconsistencies that we have found. There've been sudden spikes, and then in terms of the data formats that we got, some of them were just scanned documents, some PDFs which we have actually typed in. I'm just the representative. There's a lot of back and work that has gone into the exercise, that has gone inside to create something like this. So there have been we have found some very large discrepancies in terms of the numbers. There has been different methodologies which are used to calculate losses, efficiencies, costs, which, we try to streamline, and taking Central Electricity Authority's numbers and using their methodology to calculate for all the other discoms. And then definitely, a lot of other kind of challenges that we have. But I think basically, again, going back to the objective that we had for this website was to actually make it as a platform where any kind of user, any kind of stakeholder, whether it's my financial community stakeholder, whether it's my policymaker, which is at the state level or at the national level, or, or my funder, for that example, philanthropic funding that is getting into India, and further, even the media folks or the consumers, everybody is able to use it. And whether it's my modeling experts, my researchers. So we wanted to actually create this kind of website. It's not only for, one community, but is being used by a variety of, and just picking on some anecdotal evidence that over the years that we have gone in and had actually given us courage to, go ahead and keep on adding layer by layer to this platform was our biggest supporter, Niti Aayog, who came up, and they were very excited to see this project. And they actually said that this is something that, we should have done that, and something that they were happy to take on. And they said that, they wanted to add in more parameters so that they can make it as a platform which is centrally seen by all the stakeholders in India, and how it can be made more big. So definitely, and while it's still in the process phase, we receive a lot of requests from them, which is now informing their inputs on which they're creating documents for the Prime Minister's office submissions and other internal modeling exercise that NITI does. Then additionally, if I have to take example of a very like the outcome that actually that we have seen is that, last year we were approached by one of the philanthropic funder, and they wanted to understand based on the data in terms of the emissions, and the kind of funding sources that they have, which sector, which part of the state that the investment cycle should cater to. So really, inform a lot of, so data is something that is, ready data is being used by them, which they are using it directly from the database, and they don't really have, because we all know that the funding community is very sharp on, low on staff and people who are working. So they get those numbers very, very, even for example, the financial community. So when we started with the work on the generation side, so this was being, so we had this very good person from SBI who actually promoted our website, and they were actually using their data on renewable energy units and power plants that we were putting to actually provide that for the screen, first screen or screening of projects that they're getting, in which areas they're coming, because we also built in the land component, a little bit of forest component. So they were able to understand some parlance of the development sector, some understanding, which generally we think that everybody understands power sector, but I think, this brings in more holistic and if I have to say more common man can also understand some of the elements, at least on the homepage. And then it deep dives into further where, you get data sets at district, at granular level, whichever, or at technical level, whatever you need. Then also, lately, we have been actually approached, and we have been trying to talk to a few stakeholders at the state level where, the environment department is using this database for their strategy, for their net zero modeling exercises at state level that they want to do it. And so that is something and we have been receiving. And then in the media, we have folks who actually take ready data, ready graphs from this particular website to actually inform in the wake of the UNFCCC convenings, and when they want to put the India chapter out in terms of what is the development, what are the pipeline coal power plant, what is the number of retired capacity in India. So they just take, they don't have to, look at and not publishing wrong numbers, because all our database is government backed. So that really is something that we have been doing. Then going forward to your second question, if I have the time. Yeah.
Maybe briefly. Yeah. Thank you.
Yeah. So just on the second part of the question, I think, yes, I feel that data is the key for using or for control and monitoring, as well as for forecasts and any kind of prediction. So these are the two basic uses that I see for data. And definitely, as we are paving the way to facilitating an energy transition, whether it's an energy transition or whether it's a water level, all of us needs, it's not just a technology that needs as an enabler or a finance that, it's actually a transformation that needs to happen at an organization level, at a systemic level. And data is something that is going to drive all of this. So it's basically a transition that Vasudha's, that this ICED, basically the revised name is India Climate and Energy Dashboard, is trying to bring in, is that where we are looking at more quality data, which is meeting its relevance, which is meeting its completeness, because a lot of time what we have is we have the data, but it's not complete. A lot of times we have the complete data, but it's not formatted in the manner that can be used. So we are trying to meet all of them together. And I really feel that some of it in terms of where we are now trying to link on the climate and economic indicators in terms of its GDP, in terms of its per capita income. I think I'm sure that it's not going to look at only a CAGR extension of electricity demand forecast, but it's also going to take in use the other kind of end user parameters that has an impact on things. So it's going to help us in getting more informed assessments, and at the end of a better policy, and once there is better policy, I'm sure there is more investor confidence and there's data. So I'm sure that this is together is going to make a great value add to the entire fraternity of our energy sector and climate sector.
Great. Thank you so much, Brenda, for all of your responses. So now just keeping a watch on the time, I think we can take a few audience questions if people would want to either unmute themselves and ask a specific question. I see a few that are mentioned in the chat, but I think Lucas has responded to them. And in response to one of the questions about the solution, so all of WRI's work is, by extension, the collaboration that we had with Lucas's team is open access. So this is available for everyone to see. There are certain restrictions at this point because we are going through some review to have a publication out, but all of the material that Lucas was sharing is available open access for people to view and use and collaborate on further as well. So if anyone else has further questions, then I just request you to please raise your hand, and then we can call upon you to ask. All right. So yeah, Lucas, there is a question for you.
I see. So the question is, how do we include extreme climatic phenomenon data, so the monsoon season, for example, in our water level prediction? Yeah, this is really important. So I'd say there's probably two ways that this gets included. One is that we are using forecast data, right? And so from what the judges told us in the competition, this was something that was fairly unique to compared to the other hackathon entries. So not only is our model conditioned on historic data, but it's also conditioned on the next 15 days of forecast. So and so yeah, this gives us a misalignment between the 90-day forecast period and the only 15 days of data that we have, but that's why we use this like multiple sequence model. And so if there is sort of a climatic extreme, like the onset of the monsoon, for example, then that would be captured in the forecast data. And so it's important, which is why I think I raised this example of, maybe the most important thing is actually is predicting when that date begins, but that wasn't what we were focusing on. And so we would hope that we would see that sort of thing in the forecast data itself. The other thing that I should say is we conditioned on the day of the year. So we wanted to provide the model with some ability to have some mean reversion. So, which would allow to say, okay, by this time of the year, the usual, there's usually this much like water that flows out of the reservoir, for example. And so at least as a starting point, it would have that a 10-year mean to draw on as like the average value, and then it could kind of nudge that up or down based on the historic conditioning and the forecast data. So I think, yeah, we could probably look closer at the real extremes of data. We trained our model on about 7 years of data, and then we had 2 years for cross-validation and 2 years for test. And actually the training was a little bit less. It was more like 6 years because there was a year of corrupted data. So, in that amount of time, I think it's difficult to capture, the most extremes. And then, but you could also, and we didn't do this, but we could also condition our model to be weighted towards predicting those extremes better. So I think there's a lot that could be done. But for the most part, yeah, the forecast and the climatic mean reversion, I think, captured a lot of that.
Yeah, Lucas, I think the next question's also directed to you. It's about the model.
Which
were the most sensitive
parameters that the model was sensitive to? Could you see this model working in any geography? Another really great question. Yeah, I think we only really had 2 parameters. We only had temperature and precipitation, and the model was quite sensitive to both. And also to the day of the year. So those were like the 3 input pieces of data that went through the 3 different time horizons: the historic period, the forecast period, and then the prediction period. And so I couldn't really tell you which of the 3 was the strongest. Because I don't think the answer would be particularly simple, because it would also vary between the different basin networks. And working in any geography, we hope so. There will be, one of the other questions was about, some anomalous reservoirs and such. And there certainly were reservoirs that were where we had stronger or weaker performance. And so I think it does depend quite a lot on local conditions, but the real beauty of this computational hydrology approach is that you don't need to have a ton of in situ data about the land cover and the slope and the geology and whatnot. And actually, one of the things that we're interested in doing now as a follow-up is going back and adding that in situ data where we have good global products like land cover, for example, and slope, because any more information that the model has, the model is going to make use of. So actually, now that we have this sort of baseline machine learning approach, it'd be interesting to go back and see how much better we can do when we have that in situ data, and the model doesn't have to spend a lot of its available information learning those parameters. So it'd be interesting to go back and do that, but only where those products are global. I think the great thing about this is that it's a global approach we can take. And some of the other speakers have spoken quite a bit about Earth observation, and we do that, but with my startup we do quite a bit of that as well. So yeah, I think that's the next approach, which is making this more generalizable across different geographies.
Yeah, if I could just add to that, because I can see, for example, there are these droughts all across the world, but there was a particular focus right here in Europe. The French were very much sensitive to that their nuclear power stations were no longer being able to be cooled, or they had to shut down a bunch of them because they were no longer reaching safety levels. So could you see this being a solution for those operators? Yeah.
That's a very specific solution. I think the predictive power is there across geographies. Whether it will be sufficient for those operators. One thing, we're doing a project with the World Food Program at the moment, looking at the difference between using a standard precipitation index and then using a sort of what we're calling a hydrological drought index. And so precipitation index, how much rain is there likely to be in the next 30 days relative to the historic amount of rain. And then what we're working on is, okay, let's use that, but also let's understand how much water is available currently in reservoirs, in the groundwater, and then let's come up with a new index. So I think this, this kind of approach, should be, well, if they're not doing it already, it should be quite relevant to them. In terms of like an incremental value over what they're doing already, I'd be curious to know. But I mean, we think this method is pretty extensible.
Thank you so much, Lucas. Thank you very much, Lucas, for taking the questions. And I'm sure there's a lot of interest to continue engaging. But unfortunately, we are at time. And I just want to take a couple of minutes to just give a bit of closing remarks. And essentially, I want to, first of all, offer my thanks to all of the speakers who really spent time today, and also at all of the prep sessions earlier. And you have been so generous with your time, so really thank you so much. To Vrinda and Lucas especially, thank you very much for preparing and sharing all of your material and work at this session. Thank you for putting in the time on that. In addition, I would also like to thank my colleagues at WRI, Madhura, Anu, Samantha, and Samrat, who have been working extensively behind the scenes for this event, and actually to get the dashboard up and running as well. So thank you to all of you for your support and guidance. To the Vistar team, who actually put the dashboard together and have collaborated with Vasudha Foundation and us in putting together the visuals that we saw in the video. Please feel free to use the link and go check out the dashboard as well. And to our very supporters who from what we heard from Deepak, that there has been a long history of support for this sort of work, who have believed in this work and really supported us and brought us to this point where we are able to work on developing this predictive model, including the Rural Climate Fund, who are co-conveners for this session. And again, my thanks to the World Water Week organizers for giving us this platform. To all of our viewers here today, and hopefully others who see the recording later, please follow our work, and you can visit the Water for Power microsite that we have. Follow our work along with the microsite and on social media. Look out for our hashtag Water for Power. Please interact with the dashboard, which is now live on Vasudha Power Info Hub's Water for Power beta version. So we look forward to engaging with many of you going into the future. And hopefully these efforts that we have put in and developed this predictive model is going to be something that really helps support the transition in the power sector that we hope is will happen, and that we believe is really required urgently as well. So thank you again to all of you. Have a great rest of the day. Thank you.
Thank you.
Thank you. Bye.
Bye.
Thanks so much.